The story of relativity begins with a question that sounds almost too simple. How does the universe really work when things move very fast, or when they sit in the presence of something as heavy as a star or a planet? For centuries, we thought we had the answers. Newton had given us his laws of motion and gravitation, and for everyday life, those laws worked beautifully. They explained why apples fall from trees, how cannonballs arc across the sky, and why the moon orbits the Earth. But Newton himself admitted that he did not know the deeper why. He could describe gravity, but not explain its true nature. That mystery would remain unsolved until a young patent clerk named Albert Einstein began to wonder about light, motion, and time. His curiosity led him to a set of ideas so radical that they reshaped our understanding of space and time themselves. This is the story of the theory of relativity, explained in simple words. Let's start with special relativity, which Einstein published in 1905. Imagine you are sitting on a train moving smoothly down the tracks. You toss a ball straight up into the air, and to you, it comes back into your hand. Everything seems normal. But someone standing on the platform sees something different. To them, the ball does not go straight up and down. It follows a curved path because the train is moving forward. Both views are correct. The ball's motion depends on where you are standing. That seems obvious enough. But now imagine light instead of a ball. If you shine a flashlight on the train, both you and the person on the platform measure the speed of light. And here is the strange thing. You both get the same answer, even though one of you is moving relative to the other. This is not what our intuition would expect. If you are running toward a car's headlights, you expect the light to reach you faster. But experiments showed that light always travels at the same speed, no matter what. Einstein took this experimental fact seriously and built his entire theory around it. If the speed of light is always the same, then something else in our understanding has to bend, and that something is space and time. From this single insight, Einstein realized that time does not tick at the same rate for everyone. If you are moving very fast, your time runs a little slower compared to someone standing still. This is called time dilation. The effect is tiny at everyday speeds, but at speeds close to light, it becomes dramatic. Imagine twins. One stays on Earth, and the other travels on a spaceship at near the speed of light. When the traveler returns, they will be younger than their twin. This is not science fiction. It is a direct consequence of the mathematics of relativity, and it has been tested with atomic clocks on airplanes and satellites. Time is not universal. It is woven into the fabric of motion. Alongside time dilation comes length contraction. To an outside observer, an object moving very fast will appear shorter in the direction of motion. The faster it goes, the more it shrinks. These effects together mean that space and time are not separate things. They are two aspects of one deeper reality, spacetime. In special relativity, space and time are interwoven, and the geometry of spacetime dictates how events unfold. This is why we talk about the relativity of simultaneity. Two events that appear to happen at the same time for one observer may not be simultaneous for another who is moving differently. There is no absolute clock ticking for the universe. Each observer carries their own. This might sound abstract, but relativity has practical consequences. Consider the Global Positioning System, or GPS. The satellites orbiting Earth are moving fast, and they experience slightly less gravity than we do on the surface. Both effects, special relativity and general relativity, cause their clocks to tick at a different rate compared to clocks on Earth. If we ignored relativity, your phone's GPS would be off by kilometers within a single day. The fact that your navigation works at all is proof that Einstein was right. But special relativity had limits. It worked beautifully for constant motion, but it said nothing about acceleration or gravity. Einstein kept thinking. He imagined what it would feel like to ride in an elevator in deep space, far from any planet or star. If the elevator were accelerating upward, you would feel pressed to the floor, as if gravity were pulling you down. But if you were in an elevator on Earth, you would feel the same force pressing you to the floor because of Earth's gravity. How could you tell the difference? Einstein called this the equivalence principle. Acceleration and gravity are two sides of the same coin. This simple idea was the seed of general relativity. General relativity, published in 1915, was Einstein's masterwork. Instead of treating gravity as a mysterious, invisible force, he reimagined it as the shape of space-time itself. Massive objects like stars and planets bend the fabric of space-time around them. When smaller objects move nearby, they follow the curves of this geometry. What we experience as gravity is just objects following the straightest possible path in curved space-time. To visualize this, imagine placing a heavy ball on a trampoline. The fabric dips, and smaller balls placed nearby will roll inward. They are not being pulled by the ball directly. They are following the curved surface beneath them. Similarly, Earth orbits the Sun not because the Sun is pulling it with an invisible string, but because the Sun's mass curves space-time, and Earth moves along that curve. One of the first tests of general relativity came in 1919 during a solar eclipse. Einstein predicted that light from distant stars passing near the Sun would bend slightly because the Sun's mass warps space-time. Astronomers measured the effect, and the results matched Einstein's prediction perfectly. Overnight, he became a scientific celebrity, and relativity became a cornerstone of modern physics. General relativity also revealed some astonishing possibilities. If space-time can bend, then it can also stretch or shrink. The universe itself can expand, as we now know it does. The theory predicted black holes, regions where space-time is curved so extremely that not even light can escape. At first, even Einstein doubted these could exist in reality. But decades later, astronomers found strong evidence: stars orbiting invisible companions, X-rays emitted from collapsing matter, and most recently, gravitational waves rippling through space as black holes collide. In 2019, humanity even saw the first image of a black hole's shadow, a dark circle surrounded by glowing gas, confirming once again the power of Einstein's vision. Speaking of gravitational waves, this was another bold prediction of general relativity. If massive objects accelerate, like two black holes spiraling toward each other, they should create ripples in space-time itself, spreading outward at the speed of light. These ripples are unimaginably tiny, stretching and squeezing space by less than the width of a proton across kilometers. Yet in 2015, the LIGO Observatory detected them for the first time. Two black holes had collided more than 1 billion light-years away, and the faint tremor reached Earth. It was as if Einstein had whispered across the cosmos, a century after he first wrote the equations. But relativity does more than predict exotic objects. It changes our very picture of reality. In Newton's universe, space and time were like a stage, fixed and unchanging, on which matter acted out its play. In Einstein's universe, the stage itself bends, stretches, and interacts with the actors. There is no separation between space, time, matter, and energy. In fact, Einstein showed that matter and energy are interchangeable, expressed in the most famous equation of all, E equals mc squared. This tells us that even a small amount of mass holds enormous energy. This principle explains the power of nuclear reactions in stars and in reactors here on Earth. The sunlight warming your skin is a gift of relativity. Hydrogen fusing into helium, mass turning into energy, shining across the void. Yet relativity also leaves us with puzzles. It does not blend smoothly with quantum mechanics, the other great pillar of modern physics. Quantum theory governs the microscopic world of atoms and particles, while relativity rules the cosmic scale of stars and galaxies. Each theory works beautifully in its domain, but together they clash. Reconciling them is the challenge of a future theory, perhaps involving quantum gravity, string theory, or some new idea we cannot yet imagine. Einstein himself spent his later years searching for such a unifying theory, though he did not succeed. In a way, he left us not just answers, but also the deepest questions. Despite these mysteries, relativity remains one of humanity's greatest intellectual achievements. It tells us that time is not absolute, that space can bend, that the universe is dynamic and alive. It explains the orbit of Mercury, the expansion of the cosmos, the dance of black holes, and the passage of light through curved space. It reshapes our everyday technology and expands our imagination of what is possible. To put it simply, relativity shows us that reality is stranger, subtler, and more interconnected than we once believed. Time is not a steady drumbeat. It is elastic, stretching and slowing depending on motion and gravity. Space is not a flat emptiness. It is an active fabric, curving around mass and energy. And we, small creatures on a pale blue dot, are part of this vast, flexible tapestry. So the next time you look at the night sky, remember, the starlight reaching your eyes has bent and curved through space-time, shaped by countless masses along the way. The GPS on your phone works because satellites feel time differently than you do. And the very energy that lights the stars flows from the same principle that binds space, time, matter, and energy together. Relativity is not just a theory written in equations. It is the story of the universe itself, told in the language of space and time. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. With relativity, we glimpse that strange comprehensibility. We see that the cosmos is governed not by arbitrary forces, but by a deep, elegant structure. Space and time are not passive. They are dynamic, and in their dance, galaxies swirl, stars collapse, light bends, and we find our place in a vast, curved reality. That is the gift of relativity, to remind us that the world is more mysterious, more beautiful, and more interconnected than our common sense might suggest. And that, in trying to understand it, we too are woven into the fabric of the cosmos. Remember to subscribe to the Cosmic Chronicles channel and turn on the bell icon so you don't miss any more videos.